Welcome back to Sec 1 Geography. This is Video 7, the water budget. This video builds directly on the water cycle and water distribution we covered last time. We are now going to look at how we measure whether a place actually has enough water at the right time of year. Let's get started. Let me start with a concrete example. Picture a grape farmer in southern France. In January, the rain pours down, 85 millimeters in a single month. But grapes don't need water in January, they're dormant. The farmer does not need that rain right now. Jump forward to July. The summer sun is blazing. The vines desperately need water. But July in southern France gets barely 2 millimeters of rain. Almost nothing. The farmer's problem is not how much it rains. It is WHEN, it rains, and whether enough water is available during the months it is actually needed. That mismatch between when water arrives and when it is needed is exactly what the water budget measures. Let's learn how. Here is what we are covering today. Look at the roadmap on screen. Chapter 1 is the water budget definition and formula, including the most common WAQ1 mistake. Chapter 2 covers surplus, deficit, and the soil moisture buffer, including the 2-mark mechanism for WAQ3. Chapter 3 teaches you the 5-step method for reading any water budget graph, with location M as the worked example. Chapter 4 applies this to location N, a monsoon climate, and shows you exactly how to structure the 3-mark WAQ2 answer. 6 marks across 3 questions. This video addresses every single one. Before we look at any content, let me flag the 3 mistakes that cost students marks on this topic. Mistake 1. Confusing the water budget with the water cycle. The water cycle, which we covered in VO6, describes how water moves. The water budget is a calculation, input minus output. They are completely different things. If your WAQ1 definition describes the water cycle, you will score 0. Mistake 2. Identifying surplus and deficit periods without quoting any figures. Every mark in WAQ2 requires specific months and specific values. The surplus occurs in the wet season, no mark. The surplus runs from May to September. In July, P equals 210 millimeters and ET equals 100 millimeters. That is a mark. Mistake 3. Explaining that persistent deficit causes water stress by writing, "There is less water." That is the outcome, not the mechanism. The marks require you to explain soil moisture being drawn down and exhausted, and then the consequences for rivers and groundwater. We will build that chain step by step. Here are the 3 WA questions this video prepares you for. WAQ1 is 1 mark. Define water budget. It must include the input, the output, and the idea of balance. WAQ2 is 3 marks. Using a data table, describe the surplus and deficit periods. Every mark requires specific months and figures. WAQ3 is 2 marks. Explain why a persistent water deficit leads to water stress. The soil moisture mechanism is both marks. 6 marks in total. All 3 questions are covered directly in this video. Let's start with Chapter 1. Chapter 1. What is the water budget? The water budget is a comparison. It measures whether a place receives more water than it loses or loses more than it receives. To understand it properly, we need the definition, the formula, and the distinction between input and output. Here is the definition and the formula. Read with me as it appears on screen. The water budget is the balance between the amount of water coming into an area through precipitation and the amount leaving through evapotranspiration. The formula, water budget equals precipitation minus evapotranspiration, or simply P minus ET. If the result is positive, P is greater than ET, we have a water surplus. More water arrives than leaves. If the result is negative, ET is greater than P, we have a water deficit. More water leaves than arrives. Write this formula down. It is the foundation of everything in this video. Let's be clear about what input and output mean. Look at the 2 columns on screen. On the left, the INPU. Precipitation is all water falling from the atmosphere, rain, snow, sleet, and hail. This is what comes in. On the right, the OUTPU. Evapotranspiration is the combined water loss from an area through evaporation from surfaces. the ocean, soil, rivers, and transpiration from plants releasing water through their leaves. This is what goes out. Water budget equals what comes in minus what goes out. If more comes in than goes out, the result is positive, surplus. If more goes out than comes in, the result is negative, deficit. Simple. But this distinction, input versus output, is exactly what WAQ1 tests, and it must appear in your definition. Now let me address the most common definitional mistake before we go any further. Look at the comparison on screen. The water cycle and the water budget are not the same thing. The water cycle, which we covered in the previous video, describes the movement of water, evaporation, condensation, precipitation, infiltration, surface runoff. It is a process. It keeps going continuously. The water budget is a measurement. It compares how much precipitation comes in against how much evapotranspiration goes out. It tells you whether a place has a surplus or a deficit at any given time. It is not a description of water movement. If your WAQ1 answer describes the water cycle, it will score 0. The budget is the comparison, P minus ET, not the cycle. Chapter 2, Surplus, Deficit, and Soil Moisture. This chapter builds the mechanism you need for WAQ3. What actually happens when P is greater than ET? What happens when ET is greater than P? And what role does soil moisture play as the bridge between the two conditions? Let's go through it. First, the water surplus. This is when precipitation exceeds evapotranspiration, P greater than ET. Look at the diagram on screen. When more water arrives than the area loses, the excess has to go somewhere. It goes into soil moisture storage first. The spaces between soil particles fill up with water. The soil becomes progressively wetter. Once soil moisture is full, the surplus continues to flow. It feeds rivers, river levels rise, it recharges groundwater, aquifer levels recover. The result during a surplus period, reliable water supply. Rivers are full, groundwater is topped up, soil is moist, crops and vegetation thrive without irrigation. Surplus periods are associated with the wet season, cooler months when evapotranspiration is naturally lower, and climates that receive reliable high rainfall. Now the water deficit. This is when evapotranspiration exceeds precipitation, ET, greater than P. Look at the diagram on screen. When more water leaves than arrives, something has to give. The area cannot simply receive less water and have everything stay the same. The soil moisture reservoir begins to be drawn down. Water stored in the spaces between soil particles is gradually used up. As the deficit continues, rivers receive less water from soil and groundwater. River levels drop. Groundwater is not being recharged. Aquifer levels fall. The longer the deficit, the more severe the depletion. Deficit periods are associated with dry seasons, hot months when evapotranspiration is high, and semi-arid climates. Here is the crucial concept: soil moisture as a buffer. Look at the diagram on screen. Think of the soil as a temporary water tank sitting between the sky and the rivers. During surplus months, that tank fills up. The soil stores excess water. During deficit months, that tank is drawn on. The stored water compensates for the gap between precipitation and evapotranspiration. The key point, soil moisture, is limited. The tank has a finite capacity. If the deficit continues long enough, soil moisture is eventually exhausted. The buffer is empty. Once that happens, look at the chain. Rivers run lower and lower because there is no soil moisture feeding base flow. Groundwater levels drop because there is no recharge. Water supply falls below what people, farms, and ecosystems need. That is, water stress. This chain, persistent deficit, NAMA soil moisture, exhausted. NAMA soil moisture exhausted, NAMA soil OBO, water stress, is the full 2-mark answer to WAQ3. Keep it with you. Let's make the WAQ3 chain explicit. Look at the screen. ET is greater than P continuously. The area loses more water than it receives. This is the starting condition. Step 1. Soil moisture is drawn down and then exhausted. The buffer between the sky and the rivers is gone. That is, mark 1, the mechanism. Step 2. Rivers run lower as base flow disappears. Groundwater levels drop as recharge stops. water supply becomes insufficient for human use, agriculture, and ecosystems. That is water stress. That is mark 2. 2 steps, 2 marks. Both require a cause linked to an effect. There is less water, so there is stress. Scores 0. It skips the mechanism entirely. The marks live in the mechanism. Chapter 3. Reading a water budget graph. This chapter gives you the 5-step method for reading any water budget graph or data table, the skill that WAQ2 tests directly. Then we apply it to a real worked example. Here are the 5 steps. Follow along on screen. Step 1. Find the precipitation value for each month. On a graph, this is usually shown as bars or one of the 2 lines. In a data table, it is the P row. Step 2. Find the evapotranspiration value for each month. On a graph, this is the other line. In a table, it is the ET row. Step 3. Compare P and ET for each month. If P is greater than ET, that month is a surplus month. If ET is greater than P, that month is a deficit month. Simple comparison, month by month. Step 4. Find the crossover points, the months where P and ET are approximately equal. These are the transition points between surplus and deficit periods. Step 5. State the surplus period, the deficit period, and quote specific months and figures. This is where the marks are in WAQ2. No figures, no marks. Every time you look at a water budget graph or table, run through these 5 steps. Let's apply them now. Look at the data table on screen. This is location M, a Mediterranean-type climate. 12 months of precipitation and evapotranspiration data. Before I walk through the analysis, take 30 seconds to look at the numbers yourself. Notice where P is larger than ET and where ET is larger than P. You should be able to see the pattern. January, P8 5 millimeters, ET 20 millimeters, ET 20 millimeters, P is much larger, surplus. July, P 20 millimeters, 30 millimeters, 30 millimeters. ET is dramatically larger, deficit. January receives 85 millimeter and barely loses 20 millimeter through evapotranspiration. July receives almost nothing, just 2 millimeter, while the summer heat drives evapotranspiration to 130 millimeter. Look at the color-coded table. Green cells, surplus months. Red cells, deficit months. January through March, green. April through October, red. November and December, green again. And notice the budget values in the 3rd row. Every green month has a positive value. Every red month has a negative value. The greatest deficit is July at minus 128 millimeters. Now let's summarize the analysis. Look at the screen. The surplus period runs from October to March, 6 months of cool, wet weather when precipitation comfortably exceeds evapotranspiration. The peak surplus is December, P 90 millimeters, December 18 millimeters, a surplus of plus 72 millimeters. The deficit period runs from April to September, 6 months of hot, dry summer weather when evapotranspiration massively outstrips precipitation. The greatest deficit is July, P2 2 mil, ET 130 millimeters, a deficit of minus 128 millimeters, 2 millimeters of rain against 130 millimeters of evapotranspiration. That is a brutal imbalance. The landscape in a Mediterranean summer reflects this: dry, parched, brown. Vegetation survives on stored soil moisture and adapted deep root systems. The crossover points are in late March, when ET begins to exceed P, and in late October, when P rises back above ET as autumn rains arrive. Now let's connect the water budget to water management. Look at the diagram on screen. The location M data tells a clear story. There is plenty of water in winter and almost none in summer. The mismatch is 6 months long and reaches 128 millimeter at its peak. The management response is obvious once you see the data: store the winter surplus for summer use. A dam or reservoir fills up during the October to March surplus period, capturing the winter rain before it flows out to sea. Then it releases stored water for irrigation and domestic use during the April to September deficit period. The water budget is not just a geography exercise. It is the planning tool that tells engineers exactly when to fill a reservoir and how large it needs to be. The greater the deficit and the longer its duration, the larger the required storage capacity. Location M's July deficit of 28 mm is the calculation that drives the size of a Mediterranean reservoir. Now it is your turn. Look at the practice pause on screen. I have given you the location M data again, P and ET, for all 12 months. I want you to calculate the water budget for each month by subtracting ET from P and then classify each month as surplus or deficit. Then answer the bonus question, which month has the greatest water deficit and by how much? Pause the video now. Work through all 12 months. When you are ready, unpause and I will show you the answers. Welcome back. Let's check the answers. Look at the completed table on screen. The budget value should match these figures. I will highlight the key ones: January plus 65, February plus 50, March plus 23, all surplus, green. April plus 65. December, from here, the deficit month. From here, the deficit deepens. May Chindu 62, June Chindu 75, July is your bonus answer. The greatest deficit is 28 mm. August 21, still severe, September 68, October 70, barely deficit, the transition month. November plus 38. Surplus again. Surplus months, January, February, March, November, December. Deficit months, April through October, 7 months in total. Now look at the exam tip at the bottom of the screen. When you write up a WA answer, you must give the month name and the figures. July had the greatest deficit of 28 mm, with P2M and ETF 130 mm. That is a full mark sentence. July was the worst month. No mark. Great work. Let's move to Chapter 4. Chapter 4, Seasonal Variation and the WAQ2 answer. Now we look at location N, a monsoon-type climate, and use it to model the exact three-point structure for WAQ2. The pattern is different from location M, but the method is the same. Look at the location N data on screen. This is a completely different seasonal pattern from location M. Location N has a clear wet season and dry season, the classic monsoon pattern. Notice the precipitation values. They are very low from January to April, barely 10 to 45 mm. Then they explode upward from May, peaking in July at 210 mm, then declining through September before dropping sharply in October. Compare these to the ET values. ET stays in a relatively narrow range, 28 mm to 100 mm, with no dramatic summer peak like location M. This is typical of a monsoon climate, where the wet season is driven by seasonal winds rather than temperature cycles. The crossover points are around April-May, when P rises to exceed ET, and around September. October, when P drops back below ET. Surplus period, May to September. Deficit period, October to April. Peak surplus, July at plus 100 mm. Greatest deficit, March at minus 35 mm. Now let's build the 3-point WAQ2 answer using location N. Look at the 3-point structure on screen. Point 1 is about the deficit period. Right, the deficit period occurs from January to April, when evapotranspiration exceeds precipitation. In January, P equals 10 mm and ET equals 30 mm, giving a deficit of minus 20 mm. Named period, January to April. Specific figures, 10 mm and 30 mm. Budget value, minus 20 mm. That is 1 mark. Point 2 is about the surplus period. Right, the surplus period runs from May to September, when precipitation rises well above evapotranspiration. In July, P equals 210 mm and ET equals 100 mm, giving a surplus of plus 100 mm. Giving a surplus of plus 100 mm. Named period. Specific figures. Budget value. That is the 2nd mark. Point 3 covers the return to deficit. Right, from October, precipitation falls sharply to 60 mm, while evapotranspiration remains at 65 mm, returning to deficit conditions. By November, P equals 22 mm and ET equals 40 mm, a deficit of minus 18 mm. Named period, figures. Budget value, 3rd mark, 3 points, 3 named periods, 3 sets of figures. That is the WAQ2 answer every time. Before the practice pause, I want to address one important distinction. Look at the comparison on screen. Water deficit. What we have been discussing today is not the same as water stress, which we covered in VO6. A water deficit is a seasonal or climatic condition where ET exceeds P in a given area. It is normal in many climates. Location M has a 6-month deficit every year. Mediterranean climates are defined by this pattern. It is not a crisis by itself. Water stress is a structural chronic problem where demand meets or exceeds supply. Singapore is water stressed not because of seasonal deficits, but because of its small land area, high population density, and absence of rivers and aquifers. The link between them, if a water deficit is persistent enough to exhaust soil moisture reserves, it can lead to water stress. But a seasonal deficit in a well-managed water system, with reservoirs, dams, and groundwater management, does not automatically cause water stress. That distinction appeared in your viewing guide Q2, and it is the conceptual bridge between this video and the last one. Practice pause. Look at the WA question on screen. Using the data for location N, describe the water surplus and deficit periods. 3 marks. The data table is shown on screen, P and ET for all 12 months. Write 3 separate points. Each point must name the period, the months, and quote specific P and ET values or a budget figure. Pause the video now. Write your answer. When you are ready, unpause and I will walk through the model answer. Welcome back. Let's go through the model answer together. Look at the 3 points on screen. Point 1, the deficit period. Mark 1. The deficit period occurs from January to April when ET exceeds P. In January, P equals 10 mm and ET equals 30 mm, a deficit of minus 20 mm, a deficit of minus 20 mm. Named period, January to April. Specific figures, 10 mm and 30 mm, 1 mark. Point 2, the surplus period. Mark 2, the surplus period. Mark 2. The surplus period runs from May to September, when P rises well above ET. In July, P equals 210 mm and ET equals 100 mm, a surplus of plus 100 mm. A surplus of plus 100 mm. Named period, July figures. Budget value, the return to deficit, Mark 3. From October, P falls to 60 mm, while ET remains at 65 mm, returning to deficit. By November, P equals 22 mm and ET equals 40 mm, a deficit of minus 18 mm. Named transition. EXE. Look at the rule at the bottom of the screen. Named period plus specific figures equals a mark. Period name without figures equals 0, every time, no exceptions. Let's fix the 4 common mistakes before we close. Mistake 1, WAQ1, defining the water budget as the amount of water in an area. No mark. The definition must include input, precipitation, output, evapotranspiration, and the idea of balance or comparison between them. Mistake 2, WAQ2, identifying surplus and deficit without quoting any figures. The surplus occurs in the wet season, is a period description with no data, 0 marks. Surplus in May to September, July P equals 210 mm, ET equals 100 mm, that is a mark. Mistake 3, WAQ2, describing only one period. The question says surplus and deficit periods. Students who beautifully describe the surplus and then stop lose 2 marks. Write 3 points, deficit, surplus, and transition. Mistake 4, YWAQ3, writing, there is less water, so there is water stress, 0 marks. The mechanism is, ET continuously exceeds P. Soil moisture is drawn down and exhausted. Rivers run lower. Rivers run lower. Groundwater drops, Psi water supply falls below human needs. 2 steps, 2 marks, write the chain. 5 things to carry away from this video. 1. Water budget equals precipitation minus evapotranspiration. Positive means surplus, P greater than ET. Negative means deficit, ET greater than P. 2. During surplus, soil moisture fills and rivers and groundwater recharge. During deficit, soil moisture is drawn down. If the deficit persists, soil moisture is exhausted, and that is when the consequences begin. 3. The 5-step method for reading a water budget graph. Find P, find ET, compare each month, find crossovers, state periods with specific figures. 4. WAQ2 requires a named period plus specific figures for every mark. July, P equals 210 millimeters, ET equals 100 millimeters, surplus of plus 100 millimeters. That is the format. Period name only equals 0. 5. WAQ3 is a 2-step chain. Step 1, ET greater than P continuously, so soil moisture is drawn down and exhausted. Step 2, rivers run lower and groundwater drops, leaving insufficient water for human use. Water stress. 2 steps, 2 marks. Here is what to do next. Complete your viewing guide and revision note. All 7 key terms must be in your own words before the worksheet. Then, work through the worksheet. It uses location M data, the Mediterranean climate we analyzed in Chapter 3. Section A asks you to calculate P minus ET for all 12 months. Section B covers soil moisture changes. Use the surplus and deficit periods you identified to answer those questions. Once the worksheet is done, attempt the WA practice. 6 marks, 12 minutes, no notes. After you finish, check your WAQ2 answer. Did you quote specific months and figures for each of the 3 marks? If not, that is the fix. Subscribe. The next video covers Singapore's water management, the 4 national taps. See you there.